Hi there. Welcome to the lecture number 2 of the chapter Sound and Himanshu this side. So I hope you have watched the lecture number 1 and you have a now very good idea about the waves. Basically what is wave, and in the last lecture we had also discussion about the two types of wave, transverse wave and the longitudinal wave. Yes. We saw that in the case of transverse wave, the motion of the particles is perpendicular to the propagation of wave, and in the case of longitudinal wave, the motion of the particle is along the direction of wave. So particle do not move, I mean particle do not shift, do not leave their position and permanently shift to some other location. Instead what they do, they vibrate at their own position. So everyone was vibrating like this in the case of sound wave, and in the case of transverse wave everyone was vibrating like this, up down up down. So basically that's a wave movement and particles are vibrating up down up down. Yeah, and in the case of longitudinal wave, this is the wave motion rightwards and the particles were vibrating like this. So that's the longitudinal wave motion. Now in this particular lecture we are going to discuss about the characteristics related to the transverse wave, and which will be similar for the longitudinal wave also in some sense. So let us begin now with the chapter. So what all topics we are going to cover today? So first of all, our target would be to cover the characteristics of wave, and then after that we will be covering the production of sound wave, which we have already done, I guess. So just an introduction, and after this we'll be covering about the audible waves, infrasonic, and ultrasonic waves. I hope you have already idea about them little bit from the lower grades. If you don't know, don't worry. We are going to cover everything them in today's chapter. Okay, so let me now begin with the characteristics of wave. All right. This topic is very important because the thing is, in these topics, in this particular topic, the characteristics of waves, we are going to have the discussion about the different terms related to the wave. Okay. So now let me begin. So here you can see on the board a wave form has been shown. So which wave is this? It's a transverse wave. Particles are vibrating up and down and the wave motion is forward. So that's a transverse wave shown you here on the board. Now, what are these terms which you can see on the board, right? So to understand them, let us first of all have a look on one animation. So I'm going to show you one animation now. Just give me a second. Just a second. So I'll share the screen with you guys. Yeah. So you can see here, this is a very good animation. You can also go to this website, PHET, right? And you will find the many animations present over there. Dispersion of a prism, wave on a string, sound wave, all these animations are present there. So if you are interested in doing the digitally experiments, then you can go to this website. Manually you will be able to change the parameters there. So first of all, let us try to produce a wave. So how does it typically a wave look like? So that's how a wave is produced. So as I was talking with you in the previous section, that to produce a wave, what we have to do, suppose this is the one end of the string and other end of the string is connected to the fixed wall, right? So when I produce a certain jerk in the string, then the wave will be produced. It will be traveling forward, right? So similarly you see one thing here, this part you can see. So this is basically that one end of the string, other end of the string is fixed over here, right? Okay, so now let me try to oscillate it. So you can see this piston is being oscillated, or I can say that this end of the string is being oscillated with the help of this system, and you can see the wave is being produced. All right, let us try to do this manually also. So now I'm going to move this end of the string up. So let's see. So I'm going up, coming back, down, and then coming back. So you can see the one wave I was able to produce, right? And you can see the particles are at their own position, but they're dancing at their own position, right? So let us now have a look on the in the other way also, like producing a pulse. See, when this end moves up, the pulse is being produced. So actually, when you move the hand one time, So one wave is produced. See, it's a one wave, right? Okay, let me show you once again. First of all, you do one thing, you look at the motion of this part. It will go up, it will come down, again it will go down, it will go up. So basically that is one oscillation, going up, coming back, then going down, and then coming up. That is called one oscillation. So you see, in one oscillation, one wave will be produced. Let's have a look. Can you see that? That's a one wave. All right. Okay. So now let me go back to that slide and I'll show you how this one wave will look like. Again, I will come back to this animation. So let us go back to the presentation. Okay. So here you can see, guys, this is the one wave actually. If you start from here, this is the one wave. We can show it separately here. So that's a one wave. And now you see, if I copy this thing from here, just a second. Yeah. Now let me mark this one wave here. Okay. And if you see carefully, you keep copy pasting this thing, you'll keep getting the waves, right? So this is one wave. Then again you copy paste there. That's another wave. Again you copy paste it. That's a third wave. And again in this way, that's a fourth wave. So in this way, basically, this is one wave. And how we have been producing this one wave? When I move my hand up, down, again below, and then come back to the same position. So I started from here, I go up, I go down, and then I come back to the same position. So this is called one oscillation. Up, down, up, down, up, down. So in the one oscillation, we have produced one wave, right? Okay. So that's what we call one wave, right? Okay. So let's again have a look. How did we produce one wave? I'll show you that animation. Just a second. Yeah. Okay. So now you see, I'm going to move this part up, then I'll bring it back and then go down and then I'll bring it back. So that is called one oscillation. See, it has produced one wave, right? So you could see that. It's very fantastic. See, that's a one wave. Can you see that? These loops you are able to see, right? So one loop, this one loop. So these two loops are basically one wave. So that's how we call the one wave. All right. Similarly, you can have a continuous series of waves. If I keep moving my hand, it will keep producing the waves, right? So let me do that also. I'll keep moving my hand. See, now you can see the waves are being produced. Yeah, so they are coming back now. So the reflection is happening. So they are merging up together. Now let me settle it down. Okay. So basically, when I move my hand for the one time only, then only one wave is produced. Yeah, that's it. But when I move my hand continuously, see, the series of wave is being produced. The train of wave, you can say. Yeah, now they are coming back. Okay, now they'll reflect. Actually, what is happening now, guys? The incident wave and the reflected wave, they are meeting now. So that's why this thing is getting increased. You'll be learning this in the grade 9, interference of wave, we call it. All right. So actually, that's how we define the production of wave with the hand. And this is what we call the one wave, right? So in one oscillation, you produce one wave. So you can see here, it is continuously moving. So he is better than me. You can see the very good series of wave. Okay. So that's a series of wave, guys. You can see. Let me make it as a loose end so that it does not reflect back. Or reflection would be there anyways. No, and we can try. Yeah, no, and we can try. Just a second. No, and we should try. See, it will keep going. It will keep going forward. These pulses will not stop. So that's how we produce the wave. You keep moving your hand, it will keep going, keep going, keep going. All right. So if I keep moving my hand, that wave will being produced. But when I move my hand only one time, only one wave is being produced. All right. Okay. So that's what we define the uh, production of wave. That's how like the wave on a string is being produced. Okay. Now you remember this diagram, this animation in your mind, because I will need this here. Okay. So when I move my hand, the one wave is being produced. So basically the energy which was getting produced, let's say this is the starting point. Okay. So now the energy when I move my hand for the one time, for one oscillation, then wave travels this much distance. So basically energy has moved from this location to this location. So the distance traveled by the wave in one oscillation is called wavelength, right? So basically this thing is called wavelength. This length you can see here, that's a wavelength. All right. So this is what we call the wavelength. Distance traveled by the wave in one oscillation is called wavelength, and the symbol is lambda. That's a symbol lambda. What will be the unit of it? So it's a distance. So unit will be meters, centimeters, like that. Angstrom. Okay. In that way, we can measure the wavelength. Okay. So I hope you have understood that distance traveled by the wave in one oscillation. So energy which basically has started from here has reached here when I bring my hand back. So that's what we call the one oscillation. Okay. So energy traveled by the wave in one oscillation is called the distance traveled by the wave in one oscillation is called the wavelength. Now wave means energy. So basically the energy is being traveling forward. The disturbance is being traveling forward. That's what we call the wavelength. Okay. So now that's the wavelength, right? Okay. Again, another thing. Time taken to complete one oscillation is time period. Simple. So distance traveled by the energy in one time period is wavelength. So actually what I'm saying, that distance traveled by the wave in one oscillation is the wavelength, and time taken by wave to complete one oscillation is a time period. So in one oscillation, so my hand is oscillating, which is producing a wave. In one oscillation, the distance covered is known as what? Wavelength, lambda. And time taken to complete one oscillation is called time period. It is called time period. Capital T will be the symbol. So what is a wave speed? Very simple, guys. It's not very tough now. A wave speed. Wave speed is nothing but distance upon time. Distance divided by time. So distance traveled by the wave is lambda. In how much time? In t time. So that's the wave speed. That's it. Simple. So distance traveled by the wave in one time period is called the wavelength, or vice versa. In one time period, the distance traveled is lambda. So what will be the speed? Lambda over t. That's it. Okay. Now one more thing is there. Something called the frequency. So velocity of wave we have understood. The velocity was forward. The wave was going forward, but the particles are going up down. Energy is going forward. Propagation is going forward. If you're getting confused with this, like why particle going up down and energy is going forward, you should watch the previous lecture. I have explained it just in very much detail there. Okay. Now going ahead, now you can see when we talk about the frequency. So what is frequency? So try to understand this term. In t time, what is happening? In t time, t is basically time period. So in t time, one wave is being produced, or I can say one oscillation is being produced. All right. So in t time, we have produced one oscillation, right? So now t will be having some value. Suppose, let's say 10 second. So in 10 second, how many oscillations I have produced? One. I'm just taking one example. Okay. So in 10 second, I have produced one oscillation. So t is the time period. In 10 seconds, I bring my hand back to the same position. That is called the time period. So in that much time, the wave will cover lambda distance, wavelength. Okay. So 10 second is a time period, for example. So in 10 seconds, I'm completing one oscillation. So how many oscillations I'll complete in 1 second? 1 by 10. For 10 rupees, you get one book, right? So for 1 rupees, how many books you'll be getting? 1 by 10. So basically, that's what we call the frequency. What? That in 10 second, you complete one oscillation. So in 1 second, you complete 1 by 10 oscillation. So let me come here. In t time, you complete one oscillation. So in unit time, unit means one. Unit can be second. So unit second, unit hour, whatever will be the unit here. So in unit time, you'll be completing 1 over t oscillation. Okay. So in 1 second, how many oscillations you complete? That's what we call a time period. Oh, sorry, frequency. How frequently this process is happening. So in t time, let's say there was one oscillation. So that's the time period. Okay. So in unit time, the number of oscillations are 1 by t. That is what we call frequency. So frequency is nothing but 1 over t. Right. Now, what will be the unit of it? If time period you are putting in second, then unit can be second, 1 by second. This 1 by second is known as hertz. Hertz. It is called hertz. So frequencies unit is usually we write in hertz only. Okay, so which means that time period you have mentioned in seconds. So actually, what did we understand now? Wavelength means distance traveled by the wave in one oscillation or in one time period. Vice versa, we can also say like that. Okay, and also, what is the meaning of frequency? Number of oscillations in 1 second. That's what we call the frequency. All right. Okay. Now you see here, frequency is 1 by t. In some books, you'll find that they are using the symbol this also, nu for frequency. Nu, it's a Greek symbol. So nu or f, anything you can use for frequency. Now when I put these numbers here in this formula, so see, lambda over t is nothing but speed. All right, lambda over t is speed. Now lambda multiplied 1 by t, I can write it like this also. What is 1 by t? It's frequency. So f multiplied lambda, I'm replacing 1 by t by f. So this will become v is equal to f lambda. So this is also we call what? This another formula for speed, which we have actually derived with the help of another formulas. So that's how we should understand the meaning of term frequency. I hope you got my point now, that what is the meaning of frequency. All right. So frequency is basically number of oscillations covered by the body in 1 second. Yeah, exactly. So that's what we define the term as frequency. Correct? Okay. Now, let us go ahead with the second part. I mean, I guess you have understood what is frequency, what is time period, what is velocity of wave. Right. You see one thing. When I was moving my hand, let's go back to the animation. It would be easy for us. Yeah. Let's go back here. Yeah. Okay. So let us have an oscillation. You see this thing. Up to what maximum height these all the particles are going? I guess this reference line, this red color line you can see, all the particles are going up to this maximum height. Nobody is crossing that point. Everybody is going up to that height only. Yeah, am I correct? Any particle you pick, any particle, all the particles are going up to that height only. Similarly, on the bottom side also, All the particles are going up to that certain depth, right? Okay, I can change it. Suppose if I increase the amplitude, you can see now the particles are going up to the same height, more height. Yeah, yeah, so you can see that exactly. So now let us go back there. Yeah, so now you can see basically what was the meaning of amplitude. So maximum displacement of the particle from this reference line. So this was the starting line for them, and all the particles are going up to this maximum height. So maximum height traveled by the particle is called the amplitude. That's it. Maximum height traveled by the particle is called amplitude. In the case of sound wave, more is the amplitude, means when my voice is louder, this amplitude will be more, and when my voice is low, this amplitude will be less. So when you speak louder, the amplitude is more. Basically, this amplitude represents the loudness in the voice. All right. Okay. So now one more thing. Let us draw this waveform here. Right. Just a second. We can show a few more terms here. Let me clean this diagram first. Yeah. Okay. So this is basically we call the amplitude. This has been shown here. Now these are the points when the particle had the maximum displacement. So these points are called crest, the peak point. Right. So this is called the crest, and this is called the trough, the minimum position. That is called a trough. Okay. So if you see carefully, I said this as one wavelength. Right. Can't I say this as one wavelength? Yes, I can. Because ultimately it should be one complete wave. So you can see this is one loop, and this is half loop, and this is again half loop. So 1 plus half, total 2 loops, right? Similarly, you take these 2 points. So this is one loop, this is half loop, and this is again half loop. So 1 plus half, again 2 loops. So actually, the wavelength is not only the, we cannot say that only this is the wavelength here. No, you can take any two crest or any two trough. So distance between any two crest or any two trough is also known as the wavelength. So distance between, yeah, consecutive one we have to take. Distance between two consecutive crest or trough is known as the wavelength. That also we can say. So either you can say the distance traveled by the wave in one time period, or we can say the distance traveled by the wave uh, in one oscillation, or we can say distance between two consecutive crest or trough is also known as the wavelength. All right. Now let us do one numerical on this, and then we'll understand in more detailed way. So the question has said that a sound wave has a frequency of 3000 hertz. Okay. So frequency is given. Now you know what is Hz? It's a hertz per second. And wavelength is given as 38 centimeter. So this is in second. You should not forget this. It's 1 by second. And this is in centimeter. How long will it take to travel 2 kilometers? So first of all, you look at the units. Units are completely different. So it is said that 3000 hertz is the frequency and the wavelength is 38 centimeter. So let us calculate first of all speed. Once I get the speed, I'll multiply this with time. I'll get the distance, right? Velocity multiplied time is equal to distance. So now distance is given, time we have to calculate, and speed we'll calculate. So that's how we'll get the time taken to complete travel, to travel 2 kilometers. So how to find out velocity? Very simple. Frequency multiplied wavelength. That's the velocity. Now frequency is 3000 hertz, but remember, I should convert lambda into centimeters because everything I'll be using in meters per second. Okay, so I have converted this into meters. Now two zeros will get cancelled out and we'll get 30 multiplied 38. Let us keep it here as it is. Later on we'll solve it. All right. Okay. So 30 multiplied 38 meters per second now. Now let us go to how long will it take to travel 2 kilometers. Let's have a look. So time taken. So speed is equal to distance over time. So time we have to calculate. So that is nothing but equal to distance over speed. Now how much is the distance we need to cover? 2 kilometers. So 2 multiplied 10 to power 3. Why did I multiply with 10 to power 3? Think about it. Because it was in kilometers. And speed is how much? 30 multiplied 38. So you'll get the answer in seconds. Okay, is anything getting cancelled out? Yeah, so 10 will get cancelled out, 200. And also we can say this 2 also will get cancelled out. We can cancel out this 2 with the 38 19 times. And this 10 will get cancelled out here. So 10 to power 2 only will be remaining. So 100 divided by 19 3s are 57. These many seconds. So 1 point something it would be coming. So these many seconds the wave will take just to travel 2 kilometers of distance. Right. So it's a very high frequency. So speed is very high here. All right. Okay. So that's what the meaning of that's what the meaning of speed of a sound wave, right? And that's how we calculate it. V is equal to f lambda. Let us have one more question, theoretical question. The question is about which wave property determines the loudness. So just now I said intensity, the amplitude basically. The intensity means the loudness in the voice. How intense is the voice? So that's is determined by the amplitude of the wave. So more the amplitude, more is the loudness produced. Right? Okay. So if you see any waveform, right, as you can see the picture here. So when you see the peaks are high, you should understand that that's a more loud voice. Okay. And the second term is the sharpness in the sound. So this term is given by the pitch. So usually it has been seen that the male's voice is not very sharp, but female's voice is sharp. A kid voice is sharp, right? So there is one kid crying in the background here. If you're able to hear that, then we have a live example. So pitch is basically the determining the sharpness in the sound. If I'm saying the frequency is high, which means the pitch is high, means the voice is more sharp. Suppose, for example, Lata Mangeshkar. Now, Lata Mangeshkar voice pitch is very high. So she's producing more number of vibrations in 1 second, right? Okay. And in contrary to that, if I talk about A.R. Rahman, let's say, right? So A.R. Rahman voice is not very sharp. It's a heavy voice, which means the pitch is low. That means the frequency is low. I hope you have got my point. Okay. So pitch determines the sharpness in the sound, and basically it is given by the frequency, number of oscillations in 1 second. Amplitude gives loudness. This I guess we have already done in the previous classes, the production of sound. I guess we are all now pretty comfortable with this, that how the sound wave is being produced. So actually the sound is being produced with the help of vibrations. So we have to vibrate something, and then with the help of those vibrations we will be producing the sound. So when something vibrates, sound is being produced. So like here you can see this drum is there. So this drum will be vibrating, that membrane will be vibrating, and then it will make the medium particles also to vibrate, and those compression rarefaction will travel further. That's how the sound wave is being produced. I guess we had a very long discussion about it in the previous class, right? So you should watch that if you haven't it. Now let me come to the last topic here. That's a very simple theoretical topic. It is about the frequency ranges. So there are three frequency range which I am going to discuss with you today. One is called infrasonic. Infrasonic means the sound which is having a frequency less than 20 hertz. Means how many times the vibrations will take place? If I just take 2090, 20 vibrations per second. 20 vibrations per second, that is called the infrasonic. Right? This if this frequency is above 20,000 hertz, it is called ultrasound. You must have heard this term, ultrasound. So here the frequency is more than 20,000. Means in 1 second it is vibrating more than 20,000 times. Right? So that's a very big. And 20 hertz to 20,000 hertz, that is called the audible range. Audible range for humans. So this is basically human audible range. Okay. So 20 hertz to 20,000 hertz, it's a human audible range. So below this, infrasonic, above this, ultrasound, and in between this, humans. Simple. Okay. Now let us talk about them with few examples also. Very little discussion about their few examples as well. The infrasonic, ultrasound, and the human audible range. So I don't think human audible range will need more examples. We are the humans, right? So we itself are the examples for, like, we are able to hear this frequency 20 hertz to 20,000 hertz. Let us talk about infrasonic. Now this infrasonic sound is a very less frequency sound, right? This less frequency sound means the number of vibrations are very less, right? So number of vibrations are very less per second. This we cannot hear. Our ears are not sensitive to hear these frequencies. But what we can hear is 20 hertz above, but less than 20,000 hertz. Now this 20 hertz below frequency can be heard by the elephants, right? It can be heard by the whales also, right? And who produces this kind of frequency? Like the earthquake. During earthquake, these frequencies are being produced. So when an earthquake is starting, so in these seismic waves are being produced. I guess you will be learning this in the same grade in the last chapter. So those seismic waves are produced, and those seismic waves will be producing a frequency of 20 hertz, less than that even, 0.01 hertz to 10 hertz, depending upon the intensity of sound. All right. Sorry, intensity of the earthquake. Okay. So now basically the earthquake is producing a very low frequency. That's why we are not able to hear those movement of the seismic plates when the earthquake comes, right? Because it is a very low frequent sound. Next, I am talking about the example simple pendulum. So what is simple pendulum? That watch wala, right? So this is a simple pendulum. So this simple pendulum is also oscillating. So number of oscillations it will complete in 1 second. That frequency is also very less. So we are not able to hear that as well. All right. Now let us talk. So that's all about the infrasonic, means frequency less than 20 hertz. Means number of vibrations are less than 20 in 1 second. After this, ultrasound. So dogs, cats, rat, tortoise, they can hear this sound. And what is ultrasound? Frequency above 20,000 hertz. In fact, the bat can hear this frequency. Bat also can understand this frequency, which is about 20,000 hertz. We cannot understand. It's very high frequency for our ears, so they are not sensitive to it. So that's how the bat is able to observe the things in the night time also, if you have heard of it. So basically what bat does, it produces a sound which we cannot hear. All right. And if there is some object, suppose now consider me as a bat. Okay, now there is a object in front of me. So what I'll do, I will produce a sound which is having a frequency 60,000 hertz. Oh, sorry, let's say more than 20,000 hertz. Suppose 25,000 hertz. So now this sound wave will travel, compression rarefaction will travel. They will hit this object, and now they will reflect back. So now when they're coming back, now I am the bat, so I'll be hearing that frequency. If I hear my frequency back, what I would say, there is something. So that's how the bat is able to detect the path, that if there is some obstacle in my path or not, right? So you can see here, this bat is producing some sound wave, and now they are reflecting, getting reflected by this object, and they're coming back. And that's how the bat is getting to know that now I have to stop here now, or I should change my path. All right. So it keeps shouting and then moving. Right. So that's how the ultrasound, the purpose of ultrasound is, right? I think you have heard of it in the medical industries also. To get the images of those inner organs and all, we need the ultrasound, right? So there also we'll use the ultrasound frequencies. Okay. And one more application I'm reminding of, which is the to understand the cracks inside the metal. Suppose I have the one metal, and now if I want to see if there is any crack on the metal which is visible, then it's okay. I don't need to do anything. But if I want to see if there is any crack inside this metal in the inner portion, suppose you are a civil engineer and now you are using a beam, right, to put it somewhere in the flyover or somewhere, and now you want to check whether this beam is perfect or not. So what you have to do, you will have to check if there should not be any crack inside it. So for that we send us ultrasound wave, and those ultrasound wave will reflect back, and then you detect the data. So that's how to understand the cracks inside the metal, to understand the to get the picture of the inner organs and all. We also use the ultrasound waves only. So these are very high frequency waves which humans generally do not uh, hear them. Okay. Now the next is the hearing range. Okay. So hearing range is, just now as I told you, the range of frequency which we are able to hear. So that is what we call the hearing range. All right. So now in this hearing range, the frequencies are more than 20 hertz to less than 20,000 hertz. So we humans are also producing this frequency only. That's why another person is able to hear us. Okay. So low pitch means low frequency. High pitch means high frequency. So 20,000 hertz is the maximum pitch which can be produced by any human. Right. Okay. And beyond this, you'll have the ultrasound, and beyond this side, you'll have the, just now as we discussed, infrasonic waves. Right. Okay. So that is what about the infrasonic waves and ultrasound waves and human audible range. So I guess that's all. It was a very small lecture, right? Because most of the things about the sound wave we have already done in the previous class, so you should watch that. Okay. And this part is a little bit important, so you can have a practice of some such questions which you will be finding in your study material or in your NCERT textbook. So you must solve them. Using this only, the questions would be coming. Okay. So that's all guys now. Okay, so thank you so much. If you have any question, you please put it over the PDF. Okay, and you'll get the answer there. So thank you so much. Bye bye. Enjoy.